Hello everyone. I hope you are all doing good. My name is Diksha and I am representing Advantage Learning Solutions. It is my pleasure to welcome you to today's webinar on Fundamentals of Carbon Utilization and Storage Modeling and Simulation. We are excited to have you all with us as we will focus on how computational tools help predict, analyze, and optimize CO2 capture, storage, and conversion to ensure efficient and sustainable carbon management. It is an absolute honor to introduce our keynote speaker, Mr. Vinod Kumar. He is a reservoir engineer with master's degree in petroleum engineering from IIT IISM Dhanbad, with 6 years of experience in the industry and presently working with Olimax Energy Private Limited, specializing in classical reservoir engineering, modeling and simulation, reservoir management, and production optimization. Mr. Kumar's extensive knowledge and practical insights promise to provide invaluable perspectives for today's discussion. That's all from my side now. Without further ado, let me hand it over to Mr. Vinod Kumar to begin the session. Thank you.
Yeah, thank you, Diksha. Let me share my screen. Okay, so is my screen visible? Can anyone confirm?
Yes, your screen is visible.
Yes, sir.
Thank you. So welcome participants to this short and sweet webinar on fundamentals of carbon utilization and storage, modeling and simulation. I thank Advantage team for giving a brief introduction about me. It's a long journey with Advantage, and it will go on in future also. So let's now start with our discussion on greenhouse gases. So we are here because we need to now focus more on how to control, rather, look forward to uh, reduce emissions in the entire world. So since we can't reduce emissions, we need to look for potential storage pathways, right? So if you see, when sun emits light on the Earth's surface, some energy is captured and some energy is reflected. But since there is a layer uh, that is again reflecting back onto the Earth's surface, due to which currently we have summers being very hot and winters being very cold. So out of that, carbon dioxide plays, a major part in those emissions or those reflections that we get back onto the Earth's surface. With methane the second place. Like we all know, oil and gas industry includes methane production as the primary, component. If you take oil, for example, it's 70% methane, and rest all will be additional components like propane, butane, etc., and C6 plus. But looking at CO2 as a byproduct of several processes in the industry, be it downstream or be it upstream, we need to understand how to control or look forward to store these CO2 emissions that's prevailing everywhere in the world. So on the bottom, you can see one good table with showing CO2, methane, nitrous oxide, and CFCs with a global warming potential over a 100-year period. So it is very clear here that CO2 is not having that much potential for warming the Earth's surface, but it's because of 100 years of efforts, or not efforts directly. It's 100 years of emissions that are happening since a lot of years, and that is why currently we need to look at it very seriously. Also, with years going forward, we can see increase in Earth's atmosphere or Earth's temperature. To be honest, so world temperature rise over the past century till 2020, it's having a very high positive slope. So we need to understand how to convert these emissions into useful products, like utilizing it or storing it. So this is a very interesting letter that was written by James Black. He's a scientific advisor to Exxon about global warming, and this is in 1977. So scientist James Black gives a presentation to senior leaders of the oil and gas company Exxon, warning of climate change. So he emphasized that present thinking holds that man has a time window of 5 to 10 years before the need for hard decisions regarding changes in energy strategies might become critical. So he's indirectly telling that with increased exploration production activities, especially by oil and gas industry, these emissions might have large these emissions might have large volumes in the near future. So he wrote a letter to FG Turpin, who is the VP of Exxon Research and Development and Engineering, in 1977. So, and his subject was also the greenhouse effect. So you can see how uh, unfortunate the current situation was or is at every part of the country or even the world. It's not just about India or any other nation. So, in light of this, we need to first understand what are scope 1, scope 2, and scope 3 emissions. So, scope 1 emissions, so generally these emissions are for a certain company which is involved in several operations, not just oil and gas, any operations. So, scope 1 are the direct emissions by a company, which can be those greenhouse gases created from burning fuel to operate manufacturing plants, furnaces. Example, let's take a refinery. So, they use fuel, to operate distillation column, which separates components based on relative volatility. So, those are type scope 1 emissions. But scope 2 emissions are indirect emissions that come from sources purchased by a company in order for it to operate. Maybe it's electricity, steam, So when the company uses fuel for operating their uh, refinery, so that comes up in a part of scope 2, but burning it will come in scope 1. And scope 3 are indirect emissions that are produced in a company's value chain. For example, the company is supplying petrol and diesel to several, petrol bunks. So those come as a part of scope 3 emissions because ultimately we are using that petrol and diesel for our automobiles, no operating automobiles. So net zero is when this is when there is an exact balance between the amount of greenhouse gas emitted and are removed from the atmosphere. So currently, every company is having a or focusing more on net zero. For example, if you say SLB, SLB's logo has changed from positive to negative. So you can just observe SLB's logo. It will be like a declining line with one positive triangle and one negative triangle. So that means is they are focusing more on net zero. So of course, net zero is impossible, but at least we can go near to net zero. So now, looking at CO2 more deeply, we need to understand first of all what is CO2 as a fluid, because CO2 is a gas that we all know, but CO2 is a liquid also, and CO2 also exists as solid. For example, if you see dry ice, it is simply CO2, in your refrigerator, and CO2 is a liquid. If the present temperature is that good, then CO2 can be also regarded as a liquid or liquefied, and CO2 also can exist as gas. But there is one particular phase which is a blend of liquid and gas. It's called a supercritical phase. So when CO2 gets buried deep in depth of more than 1 kilometer, it will be existing as supercritical fluid with a lower density. You can see how density is decreasing with the burial depth, right? So the main target of all experts in oil and gas industry is to store CO2 as supercritical fluid because it exhibits a behavior that can be less risky or less you know uh, it cannot have more leakage potential if you store it as a gas or as a liquid. Store it as a supercritical fluid. So the main objective of compressing CO2 with a temperature of 31 degrees centigrade and a pressure of approx 7,400 kilopascal, which is approx 90 to 100 bars or 1,000 bars, is to have that phase transition, neither liquid nor gas, but to supercritical state. So first things first, we need to first focus on CO2 utilization. So how do I utilize CO2? As an RE, as a reservoir engineer, my objective is to enhance oil and gas production of my company, of our assets. So my focus will be on utilizing CO2 as an enhanced oil recovery agent. So what happens is CO2 can act as a miscible as well as immiscible phase. When I inject CO2 into a reservoir which has less residual oil left over, so CO2 can enhance the productivity of this producer well by enhancing the oil swelling tendency. So what happens is when we inject CO2 above a minimum miscibility pressure, CO2 can achieve miscibility with oil bank, thus enhances oil swelling because oil volume keeps increasing because CO2 is a separate phase coming and mixing with oil. So this oil can be produced and later can be separated from CO2. Again, same CO2 can be used through injector well. So in light of this, we need to understand the miscibility nature of CO2 and oil. So we need to know what is phase behavior. So you can see a ternary diagram with three components, 1, 2, and 3. So generally, a standard convention is 1 is lighter, 2 is intermediate, and 3 is heavier. So lighter means high API gravity, intermediate 30 to 40 API gravity phases, and less than 30 to 20 degrees is heavier components. So we will see what is the required composition or what is the composition of oil and at what composition of CO2 will my oil and CO2 achieve miscibility. So if I'm injecting, a slug of LPG, CO2 is itself not a single enhancer recovery agent. We can also have LPG slug or liquefied petroleum gas, which is predominantly propane and butane. So we can inject LPG also to enhance the miscibility and enhance oil swelling and achieve good miscibility with oil and good recovery. So we need to know first contact miscibility and multiple contact miscibility. So what is FCM? So injected fluid, be it any fluid, not just CO2, is miscible directly with the reservoir at the reservoir condition, which is reservoir pressure and temperature. So generally with production, your pressure depletes, right? So we need to carry out the miscibility tests in the laboratory at those reservoir pressures and your geothermal gradient, which is reservoir temperature. So we have two experiments, swelling tube apparatus and slim tube apparatus. So we try to understand what is the minimum miscibility pressure of the injected fluid that we are thinking of injecting and the in situ oil that is in the reservoir which is not able to produce. So suppose say LPG, the liquefied petroleum gas slug. So if we inject 10 to 20% of pore volume that is available for achieving good miscibility and good efficiency of sweep, followed by larger volume of dry gas or chasing water, because we need to push to enhance miscibility and enhance oil productivity. But in multi-connect miscibility, what happens is initially there is no miscibility achieved between liquid fluid and oil. So CO2 is that kind of fluid because the physical nature or behavior of CO2 and oil is different. CO2 is having a molecular weight of 44, but several oils have are multi-component mixtures, so they have different compositions of different phases. So we need to always understand what is the composition of oil and what is the minimum pressure with which I need to inject at the bottom hole. So under conditions of pressure, temperature, and composition, modifications will generate miscibility between displaced fluids and displacing fluids at in situ reservoir conditions. So CO2 flooding will be a part of multi-contact miscibility, where we have two different techniques called condensing and vaporizing gas drive. So the main objective is to achieve miscibility with the oil bank with the injected fluid, which happens with LPG. But with CO2, we need to have high pressure, that is enriched miscibility that we are targeting to achieve. So condensing gas drive and vaporizing gas drive are two categories in multi-contact miscibility, where the injected CO2 will be vaporizing because oil is heavier. So the oil is lighter. So this gets vaporized. But in condensing gas drive, the injected gas or CO2 will be getting condensed with oil because oil is heavier. So if you look at this figure, it will clear our understanding. So when I inject gas, what happens? The gas gets condensed because oil is very heavier. So there is mass transfer between CO2 and the in situ oil. What happens to achieve miscibility? There is a lot of mass transfer happening and this gas is getting heavier or getting condensed. But in vaporizing gas drive, since oil is lighter, what happens? The injected gas also gets vaporized because there is mass transfer between oil and gas. So these two processes are very well important, and the main objective of modeling and simulation is to understand how well we can achieve miscibility and get good production. So if you see miscible flooding, where I need to get a miscible zone between unswept oil zone and the two-phase zone, right? So there is diffusion zone where miscibility is happening, and there is miscible zone and two-phase zone where there is miscibility is yet to be achieved. So there is chase gas that is pushing to get more miscibility. We can also go for immiscible flooding, where we directly don't uh, want to achieve CO2 and oil miscibility, but we want to give a flood of a pushing tendency, to enhance sweep efficiency towards producer. And in partly miscible flooding, it will be a coupled process. So ultimately, we are using CO2 as an agent or utilizing CO2 to enhance oil recovery. So this is one part of utilizing CO2 in the oil and gas industry directly. Secondly, we can use it in hydrates. So gas hydrates are clathrates, which have cages of host and guest molecules. So generally, host molecule is water and guest molecule is methane. So which are called as natural gas hydrates. So natural gas is methane. So CO2 can help, uh, uh, what to say, depressurize the hydrate by taking those sites of methane that is captured. So replacement process is driven by thermodynamic difference in stability between CH4 and CO2 hydrates. So in type 2 and type 3 hydrates, CO2 is a guest molecule with methane and other molecules like N2 and sulfur dioxide. So what happens? We try to dissociate hydrate by injecting CO2, and CO2 will take the position of methane, and methane gets dissociated from hydrate. So that is very innovative technology that is I'm not sure where it is being followed, but it is actually a very good technique to capture CO2 or store CO2 and produce methane for use everywhere. So we need to understand initial destabilization where injected CO2 comes into contact with solid hydrate, and then methane release where CH4 hydrate begins to dissociate, releasing methane gas and water. And then this will enhance CO2 sequestration because new available water and injected CO2 immediately forms new more stable CO2 hydrate. And then comes hydrate cage exchange and methane production. So this is how we try to inject CO2 and try to destabilize hydrate and then produce methane through seafloor, right? So generally hydrates are very stable in permafrost regions, which are permanently frozen, right? Maybe below the seabed where we have hydrate deposits. So we try to inject CO2 there and then produce methane from them. But the main disadvantage of utilizing CO2 as an agent for producing methane from hydrates is that there is chance of leakage because prevalent temperature and pressure conditions at that seabed level. We are not sure of what happens with growing climate change possibilities. So the risk of CO2 leakage is predominant. That is the reason why it is not able to go beyond research stage. Next comes in methane production from coal beds or coal seams. So we can target sequestering CO2 in unminable coal seams where we drill a shallow wells. Generally coal seams are available at a depth of 600 meter to 1 kilometer. So we try to depressurize uh, coal seams because methane is adsorbed on the coal seam. So we need to dissolve methane from the coal seams that it gets produced. So CO2 is actually a preferential adsorber on the coal seams. So if you see the plot here, some research work is done to see with pressure what is my adsorption capacity of these two gases, CO2 and methane, on the coal seam. So you can see CO2 has higher adsorption capacity. So when I inject CO2 into coal seam, what happens? CO2 preferentially is adsorbed by the coal seam. It can release methane, out. So in this case, we are getting enhanced methane production with sequestering CO2 simultaneously. And next comes the last technique in cement industry. So this is also gaining more attention nowadays because CO2 can help, you know, uh, enhance the carbonation process of cement setting. So carbonation can be applied to fresh and hardened Portland cements, concrete, as a part of curing process. So what is curing? we try to cast cement and let it set at a certain temperature and pressure. During carbonation, gaseous CO2 diffused into concrete dissolves into the pore solution and reacts with the dissolved cementitious phases. So you can see cements. If you look at our industry, we use cementing, for isolating open hole and casing, right? So in that we have CS4 or aluminum silicates or calcium. Cements are generally calcium based minerals, right? So we can use CO2 to enhance carbonation because it forms calcium carbonate, which will help setting the cement very fast. So accelerated carbonation reaction is strongly exothermic and diffusion control process and is influenced by material properties and carbonation conditions. So what happens? The cement clinkers can be bonded very well using CO2 as a third agent with cement. So rapid strength enhancement, enhanced durability, and permanent sequestration of CO2. Because once you're constructed, it's very common that we don't dismantle it very easily. If you look at wells, for example, we can use CO2 as an agent to enhance the carbonation process, and we can permanently store or sequester CO2, right? So this is the fundamental of utilization of CO2. Next comes storage. So in storage, the main focus should be on looking at the storage sites available. So as on date, after checking a lot of researchers and practical projects happening in the world, there are six storage sites available for geological storage. Deployed oil and gas reservoirs in enhanced oil recovery for sequestration and utilization. Deep unused saline water saturated reservoirs for aquifers. Then unminable coal seams in enhanced coal bed methane recovery and other options like basalts, oil shales, and cavities. Right. So each of these options have their own advantage and disadvantage. And depth of burial also plays a major role because if you look at the previous figure where I talked about supercritical state of CO2, so CO2 is stable only below 800 meter as a supercritical fluid. But if it is above that, we can't use CO2 as supercritical gas or fluid, right? This is in clathrate hydrates, which I've already talked previously. So when we want to sequester CO2 as a hydrate, we are talking about two things. One is utilizing CO2 to enhance methane production because the methane is replaced by CO2 molecules now. And secondly, we are trying to focus on CO2 storage. So you can see on the seabed where there is clays, which are of lower strength. So CO2 diffuses, and there's a potential chance of forming hydrate with water on the clay bed, right? So we can also use CO2 to form a hydrate where water uh, captures CO2 within itself as a guest molecule. So currently in Singapore, there's a famous institute called NUS or National University of Singapore. There is a lot of research going on sequestering CO2 as hydrate, and even in southern part of India in IIT Madras. Now comes trapping mechanisms of how we should look at, when you want to store CO2, maybe say in depleted oil and gas reservoirs or aquifers. How should we look at uh, in understanding the pore scale dynamics of CO2 flow transport? So ultimate distribution of CO2 in reservoir is a result of many factors, where there are four different mechanisms of trapping, where CO2 gets trapped in the reservoir, which is mineral, residual, solubility, and structural. So structural is a very basic mechanism where it's simply storing CO2 in a reservoir structurally, right? That's it. Next comes residual, where CO2 tries to enhance, CO2 tries to form residues uh, within the bound water available in the reservoir. And later, with increasing concentration of CO2 and mass transfer, it solubilizes in the water. Then comes solubility trapping, where CO2 and water, uh, form a single phase. And then mineral trapping, where with increased CO2 concentration in the formation, CO2 will try to react with minerals in the formation. So you can see structural trap is A, where CO2 plume migrates towards top if it is aquifer and towards bottom if it is depleted gas and oil zone. And B, where residual trapping happens, where CO2 is trying to enhance, get, achieve solubility with the in situ brine, which is clay and capillary water. Third is solubility and mineral trapping, where it is soluble now in situ brine, and also it is forming, complex minerals with the formation rocks or grains, right? So there are several minerals in clays. Maybe say if you take clay or shale formations, so kaolin is a predominant mineral in shales and clays. So CO2 can form minerals or carbonates with kaolinite, and muscovites. So increased CO2 storage security is the security of CO2 storage is lower in structural and static metering because it is for a shorter period of time, because of after which residual trapping will be predominant than solubility and mineral trapping. So mineral trapping takes longer period of time to be achieved, but structural and soluble trapping takes shorter period of time to get achieved. Also, trapping contribution is more for structural trapping and least for mineral trapping. So in light of this, we need to also understand the risks during storage. So what are the geological CO2 storage risks? So the main thing is caprock integrity failure. Because if you see in this picture, CO2 plume is a volume front. When I inject CO2, because of the density difference between in situ brine and water and CO2, CO2 is less dense than water, so it goes upward. So if caprock is not having good integrity, then caprock might have fractures and microfractures where CO2 can get leaked. So we need to have a good seal. Then wellbore leakage. So CO2 can escape through existing or abandoned wells that are not properly plugged and abandoned. Third is induced seismicity. So if you are not controlling pressure during injection, it may induce secondary fractures, potentially reactivating faults and causing earthquakes. It's a microseismic event. So you can see if there's a fault which is leaky, CO2 can migrate upward and ultimately come back to surface. So unintended migration of CO2 or brine. So CO2 saline water may migrate outside the intended storage zone. And there are several geochemical reactions, especially in mineral trapping. So we need to also understand these storage risks. So again, the similar picture where in A, CO2 gas pressure exceeds capillary pressure and passes through siltstone. So it keeps migrating upward because the capillary and buoyancy forces are acting very strongly. Second, where through the fault, it can migrate upward because CO2 is lighter. Third is where CO2 can escape through gap into the cap rock into shallower aquifer and contaminate that aquifer. So generally, in several countries, if I'm not wrong, especially in India, we have groundwater aquifers from where we extract water for drinking purposes. So those aquifers can get contaminated because of this CO2 leakage. These where your injected CO2 gets migrates up dip and increases reservoir pressure and permeability of fault, and that can enhance fault slips. So generally, fault gets slipped, or it's throw and heave will get enhanced, and that may lead to CO2 leakage through the fault if it is leaky. Then E is where CO2 escapes via poorly plugged oil, old and abandoned wells. F is where natural flow of CO2 dissolves CO2 at water interface and transmits it to closure. And then through spill point, it can migrate upward on an outcrop, which is at a farther location. And F is where CO2 dissolved CO2 escapes to atmosphere or ocean. So in light of hydrates, when I want to look at CO2 storage in form of hydrate, so the risk of CO2 escaping into atmosphere or deep ocean beds is predominant. So there is one good project as a case study that you can look at is Inshallah CO2 storage project that is in Krechpa field, Inshallah, Algeria, where injection of CO2 at zero point 0.5 metric tons, millimetric ton per well per year was injected, and the formation was desalination aquifer, is carboniferous sandstone, depth of 1,800 meter, which is tight sandstone of 1 millirc, and the seal is thick shale with faults and fractures, and trap type is structural and stratigraphic because it was only for 7 years. So risks for caprock integrity concerns were there, where uplift and pressure anomalies were observed. And also they have understood that there is fault reactivation from photoseismic. They have understood that. And injection was suspended in 2011 to mitigate risk. So initially they're producing natural gas with 10% CO2. So they're trying to inject that CO2 back into the formation in an aquifer, right? So they're separating CO2 from produced gas using amine-based plant of the flue gas, and then injecting from three horizontal CO2 wells. You know, the main rationale for drilling horizontal wells is to get more, contact area between the formation water and CO2, so that they get more uh, injectivity because the permeability is very low. So tight sandstone, right? So I have kept this paper of geophysical monitoring of the CO2 film at Sleipner. This second project of Sleipner CCS project. If I'm not wrong, the injection was started in 1999. No, they have a gas condensate field producing high amount of CO2, and they want to inject CO2 back into the formation. So you can check this link for Sleipner CCS project. It's a benchmark project that every operator can follow. So now I think we are done with a lot of fundamentals on CO2 storage. Let's now look at one model in CMG. So any queries, anyone till now? Okay. So let me share this simulation tool that I have. So I keep working on CO2 storage simulation every now and then for my research work. Okay. So if you can see, it's builder of CMG, where I have tried to simulate storing CO2 in three different zones. So let me put the 3D view. Okay. So this is a traditional model that CMG gives everyone during tutorials. So what I have cut a sector. So let me show the sector also. It should be in 2D view. Sector. So this sector is what I have used for simulating the complex flow process of injecting CO2, right? So the very first thing is having a good fluid model. I need to inject CO2, right, in a supercritical state. So what I did, I prepared my fluid model using CNG WinProp. It's a PVT modeling tool. So let me go to components and EOS. Okay. So this is my EOS or equation of state model of CO2 alone itself. So what I did, I tried to import a model from generate from WinProp, right? So import WinProp generated model. So this model is what I have used to import, and that model is what I have used for simulation. So in this model, I have one well called CO2 INJ gas with constraints of surface gas rate of approx 5 into 10 power 6 meter cube per day and a max BHP of 11,000 kilopascal. So if you can remember, the supercritical condition of CO2, which is 7,400 kilopascal. So I need to have a BHP more than this pressure, because I need to have CO2 getting injected in supercritical state. Secondly, I'm trying to put maximum value of 11,000 kilopascal because I should not create fractures artificially during injection, right? And next is injected fluid. Let's check it. It's CO2, half 100%, right? Solvent. So now what I did, I've tried to inject CO2  5 years with these constraints and try to understand, I try to monitor at a later stage what happens to the reservoir after 5 years of injection to its physical nature of pressure and formation characteristics. So this model is what I have used, and these are the results that I can show you. Okay. So you can see that I'm injecting CO2 at the peak rate of 5 and 10 power 6 meter cube per day, but you can see the increase in bottom hole pressure, right? Yeah. See the increase in bottom hole pressure, it proportionately went up to 11,000 kilopascal. So now my constraint was hit. So I cannot exceed this bottom pressure. So I need to reduce my injection flow rate so that I need not, I won't fracture the formation. So you can see the pressure of reservoir pressure increase with injecting CO2, right? Let me also put yeah, cumulative CO2 injected in this. Cumulative gas SC. So you can see I'm injecting a cumulative gas of around 8 BCM, no, quite high, billion cubic meter, right? So that is what I have tried to understand how this happens. So if you look at the reservoir itself, let's look at pore scale. Now how the mass transfer is happening between CO2 and in situ water, right? Sorry, gas. So let me put sector filter USL. So this is my sector which I've used for injecting CO2. And let me go to display and put that date 30. Yes. So you can see my injection has started. So this is my pressure. Let me go for mole fraction CO2. Yes. Now you can see how CO2 keeps increasing. Okay, not this gas saturation. Yeah. So injection started and let me play. You can see how it is getting darker because saturation of gas is increasing, right? I'm injecting more CO2. And after which you can see post injection, what happened? Your plume migrated, right? So injection stopped at on 3035 and you can see how CO2 is migrating towards top of aquifer. So this is water below this gas zone, right? Now let's look at pressure. Okay. So initially what happened? The pressure is now, datum pressure, which I've kept during initialization. But after that, you can see the increase in pressure due to CO2 injection, right? So once injection has stopped, if you can see somewhere here, yeah, my pressure is around 10,000 kilopascal. But on the well bore, it is around 10,500 kilopascal. So see, I'm not exceeding the fracture pressure, which is 11,500 kilopascal approximately. So post which there is monitoring period, and you can see the decrease in reservoir pressure because there is equilibration happening, and your CO2 is trying to dissolve both with gas and with water, right? You have seen the plume that is migrating upward. So let me go for water saturation. So initially water is going down with CO2 injection, but later it had gone up. It is compressing CO2 and CO2 is like mixing with in situ gas. So this is how we can enhance the CO2 injectivity and of course miscibility with in situ gas which is depleted and enhance the storage potential in a reservoir, which we have seen now, in this simulation model. So the current advancements are, to enhance injectivity, to enhance storativity, or whatnot. A lot of things are happening in the, in both in research wise and also in execution wise of projects. So the main cost in, you know, in a CO2 storage project is getting CO2. From where do we get CO2? So I do believe that the main point is to control emissions by using CO2 as a uh, you know fluid to inject back into the formation. But yeah, we need to also have an understanding of how to capture and get CO2. From where do we get CO2? So that is the main capital expense that every company has to look at the very beginning before thinking of net zero and getting carbon credits. So that's all from my side. Thank you for your time. If you have any doubts, just let me know. Any questions, anyone? Okay, so thank you for your time. Let's meet sometime later. Thank you. Yes, David. Yes. Okay. In the case of CO2 replacement in hydrates, how much is the estimated characteristic time? Yeah. So since it is a thermodynamic, uh, process, so it depends on the current state of hydrate. For example, say if it is type 1 hydrate, predominantly host molecules are methane, right? With 6 and 5 mm rings. So when you can give good pressure of injecting CO2 forcefully, then you can reduce the characteristic time of replacement of CO2 with methane. So it depends on the physical conditions you're trying to maintain, and the proportionate thermodynamic reaction that occur during dissociation of hydrate and again association of hydrate. So your methane should come out and CO2 should go in, right? So I would say it depends on your injection pressure and your degree of dissociation due to thermodynamic activity. That it depends on.
Thank you very much.
Yeah, thank you. Okay, thank you everyone. Have a great day.